Now we're ready to look at conditional PDFs and conditional expected values in the case when x and y are bivariate Gaussian. You might remember that the bivariate Gaussian PDF formula is a super complicated thing, and chances are you can't just recall it from the top of your head. So we'll review that first. So here we go. Here's a review. The bivariate Gaussian PDF that allows you to choose the mean value for x, mu x, the mean value for y, mu y, the standard deviation, sigma x and sigma y, and the correlation coefficient, so that the density function is an exponential of this quadratic function in x and y, such that remember that this quadratic function is has level sets that correspond to ellipses of x and y. So what we saw was that when the correlation coefficient was 0 and x and y were independent, then the PDF of x and y was kind of a circular mountain of probability. On the other hand, when x and y had strong positive correlation, we saw that the scatter plots that are show you x y pairs that lie along this line where y is 0.9x, we see that mirrored in this long ridge, right? This is kind of a tall, narrow ridge of probability mass of corresponding to correlated Gaussian x and y. And then when rho was equal to negative 0.9, we saw that the xy pairs lied along the line y equals minus 0.9 x, and correspondingly, this PDF of the joint PDF was a ridge of probability that mirrored where we would see sample points scattered. Going back to the definition of the bivariate Gaussian PDF, we remind you that we have observed earlier that from this definition, it follows that X has the ordinary Gaussian PDF with variance sigma x squared and expected value mu x, and that Y also has a Gaussian PDF with variance sigma y squared and expected value mu y. And moreover, given these marginal distributions for x and y, you might be wondering, what is the conditional PDF of y given x, which of course is the joint PDF of x and y divided by the marginal PDF of x? Or you might be wondering, what is the conditional PDF of x given y, where we take the joint PDF of x and y and divide by the marginal PDF of y. The amount of algebra it takes to work out what these things are might seem kind of forbidding. The details are in the textbook. We'll present the result in the next theorem. And the theorem is kind of expertly rearranged to show you how things work. If you grind through the algebra, you find that the conditional PDF of y given x is a Gaussian PDF. It has expected value mu y with a little tilde to say it's different than the original mu y, and variance sigma y squared, also with a tilde to say it's different than the original variance of y. From this structure of this form of PDF, we know that this is the expected value, and we know that sigma y tilde is the standard deviation. But more than that, we can actually find these functions, which are functions of the observation x, in a very simple form. This mu y tilde is in fact the conditional expected value of y given x equals x. And it has the form that it's equal to the original expected value mu y plus a correction term which depends on the difference of x and its expected value. This correction term also depends on the correlation coefficient rho, the standard deviation of y, and the standard deviation of x. Each of these things plays a role. Let's think first about the case when rho is positive. In that case, if we observe an x which is bigger than the expected value mu x, then this term is positive. And if rho is positive, then we have a positive correction term to the expected value of y. And what that means is that if we observe an x bigger than the mean value mu x, then y is going to have a conditional expected value that is bigger than mu y. On the other hand, things are reversed if rho is negative. When rho is negative, if x is bigger than its mean value, then we're going to have a negative correction term, and the new conditional expected value of y given that x will be less than mu y. The other new term here is the sigma y tilde squared, the new variance of y given x equals x. This is in fact what we defined earlier as the conditional variance of y given x equals x. We use this tilde notation for it, and it also has a very simple form, but simpler even than for the conditional expected value. In this case, the conditional variance is the original variance times 1 minus rho squared. And so what this tells us is that the conditional variance of y given any observation of x is always the same for all observations x, and in fact it's always strictly less than sigma y squared as long as rho isn't 0. This is important enough to write down. If rho of xy is not equal to 0, then the conditional variance of y is strictly less than the original variance of y. If the conditional variance of y given x is very close to 0, then we know that given x equals x, y is going to be very close to its conditional expected value. And in this case, we would expect that this conditional expected value to be a very good estimate of the random variable y. A long time ago, we introduced the idea that the expected value of a random variable was our best estimate of that random variable in a mean square sense. Now we can apply that idea when we make an observation. When we make the observation x equals little x, we get a new distribution for y given x. And in the bivariate Gaussian case, this conditional distribution for y is this Gaussian distribution. And the conditional expected value of y given x is in fact our expected value of y given this observation of x. If we wanted to estimate y based on x, our best estimate of y in a mean square sense will be the expected value, specifically the conditional expected value. And finally, if we want to say, well, is that conditional expected value any good? You'll be like, well, let's look at its variance. How small is the variance of the random variable that's left once we've made the observation x equals x? And so if this conditional variance is close to 0, then we know that we have a really good estimator for the random variable y based on the random variable x. These kinds of ideas are at the core of what people would call Gaussian estimation theory. So that last bit of discussion about estimation theory maybe got us a little bit off track, but To go back, what we want to remember is that when we observe a value of x, the conditional density of y is going to be Gaussian. And you can see this graphically by taking a Gaussian PDF shown above here and kind of slicing it open and looking at the cross section. When you look at the cross section, you're seeing the conditional distribution. So for each value of x, this cross section is in fact a Gaussian cross section. The spread of this cross section depends on the conditional variance of y given x. And you might think that this example of the cross section has somehow less spread, but in fact, these conditional distributions have the same conditional variance. This smaller PDF bell-shaped curve, you'd have to normalize it to have area under the curve 1, and then the kind of the spread of this of this PDF would be the same as this one. If instead you condition on the value of y, you get exactly the same formulas for conditional PDF, conditional expected value, and conditional variance of x. We see that x has a Gaussian PDF with conditional expected value mu tilde x and conditional variance sigma tilde squared of x. And once again, we get formulas for the conditional expected value of x given y, and it's equal to the original expected value of x plus a correction term which depends on the correlation coefficient and sigma x and sigma y with their roles reversed, and the difference between the observation y and the expected value mu y. Moreover, on the other hand, the variance of x given the observation y, this is the variance of the conditional variance of x, and it's equal to the original variance of x times this multiplicative reduction factor, but the multiplicative reduction is the same for x given y as it was for y given x. It's 1 minus rho squared. When we introduced the bivariate Gaussian PDF, we did a lot of algebra to derive the marginal PDF of x and the marginal PDF of y, and to show that mu x and mu y are the expected values and that sigma x and sigma y are the standard deviations. One thing we left out, though, was showing that rho xy in the formula of the bivariate Gaussian PDF was indeed the correlation coefficient between x and y. To do this, you have to show that the expected value of x minus mu x times y minus mu y over sigma x sigma y is in fact equal to the rho that appears in the bivariate Gaussian PDF formula. So to do this, you have to evaluate this. You have a function of g of x and y, and the machinery to evaluate this kind of expectation of a function of x and y, we didn't have that machinery in chapter 5 where we stated this theorem. So now that we're in chapter 7 and we've developed ways of doing this calculation, the algebra is here and in the textbook, and maybe someday you'll want to look through it. So this slide repeats something we already said. For bivariate Gaussian random variables, learning one of the random variables results in reduced conditional variance of the other random variable. That is that the conditional variance of y given the observation of x is the original variance times 1 minus rho squared. This is less than or equal to the original variance of y, and this inequality is strict as long as x and y are not independent and rho is non-zero. The same thing goes for the variance of x given y. This reduction in variance is exactly the same factor of 1 minus rho squared. So if you're not comfortable with the machinery of bivariate Gaussian random variables, you should work out the details of this quiz, where x and y are both Gaussian with mean 0 and variance 1, but they're correlated. The correlation coefficient is a half. And you're asked what is the conditional value of x given y equals 2, and also the conditional variance of x given y equals 2. Because the expected values were 0 and the variances are 1, we can apply our formula for the conditional expected value, and we learn that the conditional expected value of x given y is in fact equal to rho y, which is y over 2. And the conditional variance of x is 1 minus rho squared, which happens to be uh, equal to 3/4, 1 minus a quarter. And so when y equals 2, the conditional expected value of x is simply equal to 1. And the point here is that learning that y is positive, and because the correlation coefficient is positive, it learns that when you learn that y is 2, you now have a new estimate for x. It's no longer expected value 0, it's expected value 1. And then you can write down a conditional PDF of x given y by just plugging in the parameters for the conditional expected value and the conditional variance.